kick things off. So here we go. I am very happy to introduce Nir Sochen to give the today's One World Minds seminar. He is a professor at the Department of Applied Mathematics at the University of Tel Aviv, and has worked over the course of his career, as he was just discussing, in a wide range of areas, including string theory, statistical mechanics, and more recently, computer vision. And I believe he has a computer vision talk for us today. And I'm looking forward to hearing it. So I'll turn things over to you and let you tell us what you have.
Okay, thank you, Mark, and thank you all organizers for the invitation. I'm very happy to be here and to give this talk. So this is not about string theory today, that will be on another day. Today I'll talk about solving PDEs by deep learning, unsupervised deep learning. Both forward and inverse problems will be solved by deep learning. And let's start. Maybe one important work. This work was done with Leah Bar, which is done a lot of work here, and actually lead this research line. Okay. So let's start from the beginning. So the motivation is PDEs. Okay, and PDEs are everywhere, right? In physics, I have a strong background in physics, as Mark mentioned. Imaging, this is image formation, image processing by all kinds of methods, diffusion, denoising, deep learning, etc. And then you have in medicine, economy, chemistry, etc., etc. So PDEs are almost everywhere, and there are many ways to tackle this problem. So let's look on some typical problem of PDEs. So U of x is the function, is basically the solution of this equation, which involves the function in its derivatives. And this is here denoted by the red U of x. And then we have coefficients, A of x and B of x, in the equation. So the A of x and B of x, they define the operator, the differential operator that acts on U. Okay? So basically the forward problem is the following. We are given the differential operator, which means that we have the A of x and B of x, which are the coefficients of the derivative. Here, A is the coefficient of the first derivative, and B of x, the coefficient of the second derivative. And we want to find the solution U of x. This is the usual way the problem is approached in undergraduate study. Okay, the inverse problems is, well, it's the inverse. Here the U of x is given, and what we would like to find is the differential operator, which means what are the A of x and B of x? What are the coefficients, the functions that define the differential operator? Actually, this is a semi-inverse problem. The fully inverse problem, which we call also tomographic problem, is where U of x, the solution, is only known on the boundary. And then we would like to find the solution at all points, and also the differential operator at all points. So, but we will proceed by steps to get to this fully tomographic problem. Okay. And the idea was to solve these problems, forward problem and inverse problem, by means of machine learning. So let's start by looking on this differential operator. This is a linear differential. Yeah, it should be linear here. This is a linear differential operator. This is a sum of derivatives up to degree m. And for each term here, there is a coefficient, A of x. U of x is the solution. here the differential operator, which is defined by the coefficient, acts on the function u of x. Okay, and oops. Okay, and now we can define the problem. We have the differential equation, which is L acting on u equal f of x, some known function, in the domain omega, which belongs to d-dimensional space. And this is a Dirichlet problem, so we have the values of the function known on the boundary of the domain. And the usual way to approach this is by numerical consideration. Usually you cannot find analytical solution. So the numerics is either by finite difference, finite element, finite volume, discretization, etc. So this is an example. On the right, you can see finite differences. So this is just putting a grid on the domain and calculating the values of the function on the vertices. In the finite elements, in the two-dimensional case, you have a triangulation of the domain, and then you put a polynomial on each one of these triangles, and you demand some continuity and differentiability from this function, which is defined in the domain. Mostly this is a linear function on the triangles, and you only demand continuity. And these two approaches, there are some other approaches, but these are the main approaches. For higher dimension, you have to have simplices instead of triangles, and it becomes more complicated. And there are a few problems with this way to go about the numerical solution of these PDEs. This is usually depends on the discretization. It may depend on the size, on the direction of the lattice of finite differences. The derivatives are computed numerically, and they are sensitive to noise. So the error of the derivatives when it is calculated in this numerical method may become large. And also interpolation and extrapolation are not straightforward. So these are the kind of problems you encounter in numerical analysis of PDEs. Okay, and the way we try to go about it is to use a neural network as the solution of the PDEs, both for the forward and the inverse problems. And the way we go about it is to, you will see in a minute, the function actually is given explicitly, and then all the derivatives can be calculated analytically. We don't have any problem of noise in calculating the derivative. It's also mesh-free, so it does not depend on the triangulation, and the domain can be anything. We are not limited by problems of triangulations, etc. Also, this framework enables adding prior knowledge of regularizations in a natural and simple way. Okay, so let's go. The basic works were done in 2017. They are on the right here. You can see the 3 papers that were pioneering this approach. And we will, I will show later what are the contributions that we did here. Okay. So let's, before doing some complicated stuff, let's start with one simple example that will demonstrate what we are doing. Okay, so let's look at Newton's law of cooling. Okay, so here it is. We are in a camp, okay, and we have a fire and we are boiling water. And the environment, so the water are boiling at 100 Celsius, and the environment is in -10, let's say. This is quite cold. And then we take off the water out of the fire, and we measure the temperature, and we would like to see how the temperature behaves. Okay, and we know how it goes. So let's denote the temperature in the environment by M, and the temperature of the water by T. And then we know that the change in the temperature depends on the difference between the temperature and the environment. And taking some numbers where K is taken to be 0.25, we have easily find the function of change of temperature with time. Okay, now let's see how we solve that with deep learning, or with learning, which is not so deep in this case. Okay, so we have the equation that the change dt, so the change of temperature with respect to time, minus k times a minus t equals 0 at all times. Okay, so let's build this network. Okay, the input is time. We have one layer with 30 neurons, and the output is the temperature at that time. Okay, this is the network, very simple. Okay, and this is the loss. The loss is simply the demand that dt minus k a minus t will be 0, meaning that the L2 norm square will be 0, and we add also the boundary condition that the temperature at time 0 will be some given temperature, like 100 in our case. Okay, and here is the 4-line code that build this loss function. This is very easy. And as you see, the T here, the temperature, is actually this network. Okay? So this network depends on the weights, which are the parameters. So we have a function with parameters omega, and now we optimize omega such that it minimizes the loss. Okay, very easy, and this is the result. So you can see here the result. The X is the output of the network, and the blue one is the analytic solution. And you see that the fit is very good. And the point here is that we can sample from time. We can put here any time, positive time, of course, any positive time that we would like. We are not limited by data. There is no data. Okay? We can choose any T. It does not have to be on a grid. It can be, in this case, this is just sample, random sampling of time. And then for each time, we try to optimize the weights of the network such that the loss will be minimized. Okay? So this is the idea. I think in one-dimensional case, this is very simple. And now I'll show how this is generalized to higher dimensions. So in higher dimension, we use actually a deep network, not so deep. In the picture, this is 4 layers. In reality, it is 4 or 5 layers, sometimes more, sometimes less, but this is not very deep network. We don't need it to be very deep. The output is simply a point in the domain. Okay, so in this 2-dimensional case that we see here, this is x1 and x2. This is just the coordinate, okay, of a point in the plane. And then we have the network, and at the end we have u, which is the value of the function at this point. Okay, so now we train the network such that the function will have the value that minimizes the loss function. And the loss function will be, of course, the PDE. So now I write here in this case explicitly u of x, okay? So what you see here in the picture, it simply has this form of the function, which are built from the weights and the biases. And the activation function here is taken to be tangency hyperbolic because we want the u to be differentiable. Okay, because we know that the solution of the differential equation is differentiable. Okay? And actually, u of x is a smooth function. So this is infinite times differentiable function. Okay? And you can see here, since we have the explicit form, we can do the derivative here. This is not a numerical derivative. This is an explicit derivative of this function. Okay. Okay, so let's now go back. I remind you that this is the differential operator acting on the function u. And we are in the forward problem, so we know the coefficients, we know the differential operator, and we are looking for the unknown function u of x. And this is the loss function, actually. So let's go over it term by term. This is the L2 fidelity term, okay? So this actually, it forces the equation up to a set of zero measure, okay? Because L2 in the continuous setup, okay? It's actually all functions which differ by a zero measure set are the same with respect to the L2 measure. So the second term is L infinity fidelity. And here this forces the equation for every x in the domain. This is not an average like the L2 fidelity. This is really at every x. Okay, and this is important, and this is one of our contribution here. And I will show later what is the difference by having this term here. The third term is the boundary condition. We know this is Dirichlet problem, so we know what is the value of the function on the boundary. So we enforce this one. And also note that this is in the one norm. So this is a robust measure, basically. So it allows some noise on the boundary as well. And the last term is the regularization, which one can add easily if we have some prior knowledge about the function. In the semi-inverse problem, where we know u of x and we are looking for the coefficients of the differential operator, then we have a similar loss function. Again, we have the L2 fidelity. Maybe I should say here that in this case, the A of x here is represented by a network, by a deep network, neural network. And then again, actually, this depends, the loss function depends on the weights of this network, and we try to minimize as usual. So we have the L2 fidelity, we have the L infinity fidelity, we have the boundary condition for the coefficient, and again, we can have a regularization if we know we have some prior knowledge about the coefficient. Okay. And now how it does work, it works by choosing randomly points from the domain. As you can see, it's not a grid, it's not a triangulation. You just have to randomly sample points from your domain and from the boundary. So the blue are inside the domain and the red crosses are on the boundary. okay? And this is why this is mesh free. We don't have any problem with non-regular shapes or whatever. And also we can go to higher dimension without the primer. Okay, so let's take an example. Let's look on an example. This is the.
Can I ask a quick question?
Yes.
What happens if you solve this way on a grid that your favorite standard finite element solver would use? Do you get comparable accuracies if instead of using?
I'll show examples and comparisons to other numerical methods. We actually we compare it to a finite element method.
Okay.
Not to a difference, but I'll show you.
Using the same evaluation points?
Well, for the finite elements, you don't have.
Yeah. Okay.
We didn't try it for finite difference.
Yeah. Okay. I was just wondering. It would be interesting to see how it would compare with the same function evaluations.
Yes. Yes, it should be interesting. I mean, it's nice here because the point is that the network is actually a continuous function of the input. A lot of time the input is given like, you know, in supervised deep learning, you have a discrete set of input points. But here you are not limited. And actually you can check the value at any point. So interpolation is not a problem at all.
And then one other quick question: how do you choose your mu and lambda parameters in your loss function? Is there?
Yes. So I'll get to that in a few minutes because I want to give the examples, and then it will be I'll give the values exactly.
Thanks. Okay.
Okay. So this is the EIT. This is just I described the problem. So this is electrical impedance tomography. And you can see from the picture on the right, you have electrode around the chest of someone. And you put actually a current on the boundary. So the skin is the boundary of the domain, let's say. And you apply some current, and then you measure the voltage on the boundary, okay? And the equation that describe the physical process is this one, okay? So this is divergence of sigma times grad u equals 0, and sigma of x is the impedance, and this depends actually on the impedance at each point inside the body. Okay, so if you know sigma of x, you have information on the body inside. Okay, so basically, EIT is about finding sigma. Eventually, this is finding sigma of x, because this is how you extract information about the biological tissue. Okay, but before getting there, let's just look on this equation. So we have this equation, and suppose that we know the values on the skin, so on the boundary. Okay. So U of x is the electrical potential. This is what we measure. And sigma of x is the electrical conductivity density inside the body. This is also inside the body. And as long as sigma is positive at all points, then U is at least 2 times differentiable. And there is existence and uniqueness theorem for this equation. Okay. And what we know is the electrical current which we apply. This is proportional to the derivative of U with respect to the normal to the boundary. And here we put it to be a cosine n time phi plus some bias. Okay, so the n count how many periods you have along the boundary, and phi is just the bias where, let's say, where 0 is. okay? And U is just the voltage on the boundary, okay? And this problem, there is a very extensive research done analytically and also numerically by the Helsinki group, by what is called the D-bar method, where they apply the Dirichlet to Neumann operator, which is, well, quite complicated mathematically, so I will not describe it, but they did a very nice work, and we will compare to the results eventually. Okay, so let's first assume first that the conductivity is known, okay? And we solve the problem with finite element method, okay? So here is the current, psi. You can see that it has 3 periods, so n equals 3 here. This is conductivity, so this is the phantom, one of the phantom that we worked with. And we solve it by usual finite element method, and we get the solution, which is the ground truth for us, is the ground truth. We need to compare our result to something. So this is for us the ground truth. And then we extract from this ground truth the values of U on the boundary. Okay, so get the U naught information from this. And now we can take sigma, we can take U naught together, and we can try to construct with our network the potential U of X. Okay, so this is what we do. We have 2 psi's that we apply, so 2 different current patterns that we apply on the boundary. We have 2 phantoms, sigma 1 and sigma 2. Okay, and we do this random sampling from the inside, the xi, and on the boundary xb on the red, and we construct this Li. Li is the operator applied to the point xi, and of course it depends on omega, on the weights, because U is the network which depends on the weights. Okay. And here is the actual functional. So this is the actual functional that we did. This is similar to what I showed before. Oops. Yes. So here, on the first term is the L2 fidelity term. So this is just the demand. The L2 demand that this operator acting on U will be 0. The second term, this is a relaxed version of the L infinity. So here we took not the one point where the error is the largest, but we took k points where the error is maximal. So the k largest errors, and we took that as a relaxed version of L infinity. And the third term is the boundary condition, the L1, boundary condition L1, and the last one is the usual regularization of the network weights. So this is the weight decay. And so the network that we took had 4 layers.
Sorry, one of the panelists wants to know how you can randomly sample inside the domain of interest in the application, the EIT.
Well, in this case, we just know the domain, right? We have the circle, so we can sample that.
But in an actual applied setting, I guess you would.
I mean, you don't have to you don't do that online, but you can sample in advance as much point as you like.
Yeah. Okay. Makes sense.
I mean, there is. I'll talk later. This is about. I mean, there is. It's not a bad idea to sample online, but it's much more difficult and complicated. and this is under current research, let's say. We
Okay.
studied the problem. But for this application, we just sample that in advance.
Yeah.
Okay. So the network is very simple. This is like 3 layers of 26 neurons, and the last one is 10 neurons. And the activation is tangent superbolic, as I said before. The optimization was Adam algorithm on using TensorFlow. It runs 12 minutes on a CPU, on a laptop of Lear, basically. Not very, it's not all night on some very strong machine. We choose 80,000 points, 1,200 points on the boundary, and you have below the value of the parameters, lambda, k, which are the top k errors, and mu and alpha. So these are the hyperparameters. Of course, I mean, you have to play a little bit to get that, but it's quite stable. It's not very, you don't have to, it's not that if you change that a bit, then everything fails. It's quite stable. Okay, so these are the results. So here you have, this is sigma 1, this is the first phantom, and psi 1, 0, this refers to, as you can see, one period and the phase is 0. And the upper row, this is the ground truth, or quote unquote, this is a finite element method. This is the best that we could do. The second one is the results of our network, and you have the SSIM and the mean square error and the PSNR with respect to the FEM and the relative error. And it's very difficult just by looking on U to understand what is sigma. But when you look on the derivative of U, so the du dx, then you see quite easily the structure of sigma comes out. And so you can see here the results here is also quite good. This PSNR of 43 dB, this is quite good. Okay, so this is the second psi. This is a different current applied with 2 periods and similar good results from training of the network. And this is sigma 2. This is more difficult. This is supposed to be 2 lungs and a liver or something like that. And again, this is psi 1, only 1 period. And these are the results, which are again quite good. Both for ux and du dx. Du dx is calculated numerically. Again, for the proposed, for the middle column, this is calculated analytically. Okay, and again, this is the second current, the same phantom, and again, we get quite good results. Okay, so now I would like to show you the difference with a network that people suggested before us. So in particular, the DGM that was published by Sirignano and Spiliopoulos in 2017 in the archive. In the meantime, that was published, of course, but I don't know, I don't have the exact reference here. But the point is that they have a similar L2 term first, and then they have a boundary term with L2, and then the usual decay term for the weights. And so there is no L infinity here. There is no way, there is no parameter that balance between the boundary condition constraint and the L2 constraint. And you see that the boundary condition is L2, not L1. And there is, of course, no regularization. Okay, so this is also something, but overall, it's quite similar to what we have. So yes, you see here, this is L2 for the boundary. And so here, this is what you see. This is the ground truth on the left. This is the ground truth. So this is the finite element method that we got. In the middle, this is our result with the L infinity norm. And the rightmost is the DGM, where we took out the L infinity. And you can see that without the L infinity, there is a distortion of of the results. Okay, then you see that the PSNR is 16.88, while here with the L infinity norm, this is 38.26. So this is really dramatic. The L infinity term is really something which is necessary to get a good result. And this is also a test that we did about comparison with DGM, where we added noise on the boundary. Okay, so this is sigma of the noise. This is the standard deviation of the noise on the boundary. And as long as the noise is not too strong, you can see that with the L infinity term, we are doing much better, PSNR-wise and SSIM-wise, and actually in all parameters. The only place where the DGM is slightly better is with very high noise. Okay. And also, from theoretical point of view, the L infinity norm is actually said that we have uniform convergence to zero of this operator. Okay, you can think about it as error or as a reminder. In both cases, you have uniform convergence with the L infinity term. And so you can see that, as I said, the L2 term minimizes the error in the integral sense or weak sense. You see, this is an average here. It's actually average over all points. And the second one is it minimizes the error in the strong sense. So it's supposed to be at every point. Okay, so we take the largest error and we push it down. Okay, and we can show theoretically, I will not go through the proof because it's too technical and takes too much time, but one can show that when epsilon, when we do iterations and epsilon converges uniformly to zero, then un, so the updated function, so because we update the weight, so we have each time un converges uniformly to the solution. Okay, so this is also, so we have also from empirical point of view and also from theoretical point of view, the fact that the L infinity term is important here. Okay, another point is that to look on the histogram of the error. So we just go over all points that we sample and we compare the distribution of the error in the DGM method in our method, and we can see that as expected, actually, the DGM has a lot of error which are relatively large. Okay, so the next thing that we do is to look on all points where the error was larger than 1.9 times 10 to the minus 5. And we just looked where are they, all these points. So you can see here on the left, you have the DGM, you have around 1,400 points, and somehow they are all concentrated in one point, and which is on the edge, one of the edge of the edges of the sigma phantom. And the result above, you can see this, it causes this alteration or distortion of the ground, of the truth, of the true function. In our case, we have around 400 points, which are where the error is big. Also, it is on this edge, on one of the edges of the phantom. It's somehow more sparse than before, and it has less effect. But this is certainly something to think about, because we can see that the errors tend to go to the edges of the phantom. So maybe a better sampling method will enhance the result even more. We don't know. This is something to think about. And this is related to what Mark asked before, because if we choose in advance the points, we cannot adapt the sampling on the fly, which maybe it's a good idea to actually have, but we didn't have until now. Okay. Selection of K. So how many points actually to choose as for the error, for the maximum error? And we try to have this, this is empirical analysis of the problem that we have. And we can see that somewhere, I don't know, between 100 and 1000, suppose is quite good. We actually took a little bit less, and we didn't see a lot of difference at the end. But this is a kind of sensitivity check, how much. You see that if we choose too little, I don't know, 10 or points or 1 point, then this is not a good choice. We need to have more points here, so it will have enough weight to move the weights to the right direction. Okay, so we can see here small k has doesn't have enough influence. Large k, we go to, this is already something like L1 norm. Okay, so we have to be somewhere in the middle. Okay, another point that we try to check is the sensitivity to the number of points, and you can see that there is a large plateau here. We worked with 80,000, but we can work with 60 or 40,000 easily with the same accuracy. Okay, so this is for the forward problem, and now for the semi-inverse problem. So this thing was not done before. And here we have the sigma of x. This is the phantom, the u of x, which is the solution of the PDE. And on the upper row, we see the phantom with different smoothing conditions. So we took the same piecewise constant sigma x, and we applied a Gaussian kernel with the different standard variation. And you can see when you look on the u of x, there is almost no change. You can, it's difficult to see. The changes in u of x are very small. So this means that we have a kind of ill-posedness in this case with respect to how much smoothness we apply to this. Okay, and here is this is what we do. We change the smoothness here, and we check the relative error, and you can see that this is bad news, basically. I mean, this is not convex. You have many minima. This is not nice. So this is where regularizer is needed, actually, to get good results. So this is how we actually implemented that. So U was approximated by the network, and so it can be evaluated at any point X. Okay, this is important because we need something here in the semi-inverse problem. U is known and sigma is not known, and then sigma is going to be represented by a network that can evaluate the value of sigma of X at any point. But in order to solve to use the PDE, we need also to know the value of U at any point. So to prepare our experiment, numerical experiment, we first found U as a network at any point. Okay? And then we took a network for sigma, okay? And we would like to find sigma on the whole domain, okay? Knowing only the boundaries, okay? We assume that sigma is actually constant on the boundary. And on top of that, we had a total variation regularization because we needed a regularization on that, and we know that in our case, the phantom is approximately piecewise constant, so this is the total variation is a good regularizer for that. So here it is. Li is the value of the differential operator on the point xi. Here, u of x is known, and the derivatives are calculated analytically, and sigma of x is a network. Okay, and this is the fidelity. This is the loss function. So we have, as before, the L2 fidelity. And we have the L infinity, we have the boundary condition for sigma, we have the weight decay, and we have the total variation on the sigma. Okay. One more thing that we can do is to, in this case, sigma, which is the impedance inside the body, is constant, but we can take many different, apply many different currents on the boundary. Okay, on the chest, we can apply any pattern of current that we would like. So the pattern is U of J, and for each U of J, so we have a different boundary condition, so we have a different solution U. Okay, so U of J is the solution for the boundary condition J. Lij is the differential operator on the Uj at the point xi. So this is Lij. So for each Uj, we can write a small loss function, which is the L2 plus the relaxed L1. Okay, and then we can compose everything in one loss function. So this is sum over J for all these solutions that we know Uj, so for the different patterns. We have the boundary condition on sigma, we have the usual network regularization, and we have the total variation on that. This is the way it is implemented. And so here we have, in the experiment that we did, we have 4 patterns. So 1 period phase 0, 1 period phase pi over 4, 2 periods phase 0, and 2 periods phase pi over 4. And this is the result that we get for the 2 phantoms. And you can see that the results are quite impressive, actually. Okay. So here we demonstrate the possibility to do some shapes, arbitrary shapes. So this is like small 3 Pac-Mans with different mouse size. And so we just apply the same thing. Here we took the same phantom, but we took out the rightmost length, so we could cut out this Speckman without problems. And so these are the results. And you can see that the results are quite good. The PSNR is 37, 43, and 39. A very good relative error. Okay, these are the du dx. You can see, you already see the sigma appearing, and again the error is very good. Okay, and this is the result of the generalized semi-inverse problem. Oops. Okay, and this is the result of the, so we have these 4 U's, we have 4 solutions, and we apply it, and we can see, I don't know what happened, it goes up and down, and you can see the solution for sigma, the recovery of sigma is quite good. Okay. So this is the case where we know U of X, so we know the potential, the electrical potential at every point on the body, and this is not realistic. What we would like actually to do is, is to do a full tomography. Okay, so we have N measurements of the voltage and of the current. The current is applied and the voltage is measured. And we have N patterns like that, but that we apply and measure. And we would like only from this boundary condition to calculate the conductivity, which is actually the tomography. This is the information that we get about the biological tissue. Okay, so we built here N network, a network for each U, each solution, and one network for the sigma, because in this case we don't know neither the U's nor the sigma. We only have boundary conditions on them. Okay? And this problem again is ill-posed. So here, for example, you see that when we change the radius of this phantom, then the U changes completely. And also the value of this circle with respect to the background may change the values of U of X. So on the small graph, you can see how the arrow changes with respect to the radius, and on the right you can see how the arrow develops with respect to the value, and you can see that both are problematic. So we need some to apply some prior or some regularization. Okay, so this is again the problem that we apply. So we have, again, as before, Uj, and Uj, the operator acting on Uj at the point xi is denoted by Lij, and then we have rho of j is the loss function for the function Uj. So this is L2, relaxed L1, boundary condition. This is the Dirichlet boundary condition as before. And then we have also the Neumann boundary condition. Okay, here we have to apply both boundary conditions. And of course, the rate decay is usual. And then we sum over all Uj's. We have also the boundary condition for the sigma, the weight decay, and the total variation prior on sigma. Okay? So this is quite complicated already. So this is okay, and this is what we got here. So on the left column, we have the ground truth for 2 phantoms that we have. Second from the left, we have our method with this function, or this loss function that I just showed you. Next to it, second from the right, we have the Muller and Sultanen. So this is the Helsinki group using the D-bar method. And on the right hand, this is for Mark, a question. This is, we try to compare it to a finite element method. So just straightforward numerical method to solve this problem. And you can see that this network, small network, does much better than the usual finite element method in all parameters, PSNR, SSIM, MSE, etc. So you have here on the bottom the references for these two methods, the Muller and Siltanen, and for this ADOS method. Okay, so we have few more minutes, so no, almost not at all. Okay. Maybe I'll just talk.
3:30 is okay.
Okay. So I want to, this is something that we did last month or so. This is eigenvalue problem. We just try to apply that to the eigenvalue problem. This was done, again, Leah Bar did that, and with a student, Ido Ben Sharon, that did a wonderful job. And the problem is as follows. We have a self-adjoint operator, and we are looking for eigencurves, so eigenvalue, eigenfunction of this operator. And then it is self-adjoint, so lambdas are real. The operator T of u is L applies to u plus lambda u equals 0. Lambdas are real, as I said. And I'll go fast. So first problem is one known eigenvalue. So I give you the eigenvalue, and you try to find u, which is the eigenfunction. So this is the u that solves the equation tau u or tu equals 0. Okay, so we apply the same ID. We have L2 fidelity, L infinity term, boundary condition. We have normalization because u equals 0 is a solution, and we don't want the solution, so we force u to be non-trivial, and we have the rate decay. And so the example that we took was u double prime plus 4u equals 0, and we took the boundary to be 0 at the points 0 and pi over 2, and the solution is just sine 2x. So we know what the solution is, we have a ground truth, and we apply the usual mechanism, and this is what we get. Okay, 100 iteration, the ground truth is the orange one, and the model output is the blue one. So this is 500, and this is 1000 iterations, and we see that we are pretty close. Okay, so this is this, and next we want to find one eigenpair. So here we don't have neither the lambda, neither the u. And the way to go about it is to define the Rayleigh quotient R of u, which is the sandwich of the differential operator by u divided by the energy of u, minus this one, of course. And it is easy to see that if u is an eigenfunction, then the Rayleigh quotient is the eigenvalue. And that the eigenfunction is a critical point of RU. This is, so if you just do a variational calculus on R of u, you find that LU plus R of u times u equals 0 is the critical point of this function, of this Rayleigh quotient. So this is actually what we put inside LU plus RU times u. So this is our operator, and we do, this is just again and again the same thing, L2, L infinity, boundary condition, normalization, rate decay, and plus a term which guarantees that we go for the smallest eigenvalues because we minimize this loss function. So we are going to find R of u, which is the smallest possible. So here again, this is the experiment. The analytic solution is 2 over pi sine kx, where k is natural number. So this is 1. Here it should be 1, the result for lambda. Okay, so here it is, iteration 1. On the left is the eigenfunction. On the right is the Rayleigh quotient, 50 iteration. And here we have 1000 iteration. And you can see that on the left, the function is sine, as it should be, and the value of the Rayleigh quotient is 1, exactly as it should be. Okay. And we have here also the standard deviation, which is very small. So next, we try to have multiple eigenpairs. Okay, and this is just applying for each eigenfunction or for each eigenpair what we did before, and demanding that all eigenfunction be orthogonal to each other. Okay? So the first one is just a sum of identical loss function as we've seen before. The only difference is here that gamma I, the coefficient of the Rayleigh quotient, is 1 over I. So this is a descending order. The value is decreasing. Yeah? And the last, and then we have a weight decay, and the last term is demanding orthogonality of all these eigenfunctions. Okay, and here again, we did the same thing. These are the values, and these are the results. So this is for 4 functions, and you can see on the left the sine function, and on the right you can see the values that we get, which is 1, 4, 9, and 16, exactly as it should be. And for 5 function, exactly the same, we get from 1 to 25. And this is the convergence. And I think that's it. So let me just conclude by saying that actually we've seen that deep learning is a very powerful tool to solve PDEs. So this is actually a new numerical scheme for solving PDEs. It is done by unsupervised learning process. And it can be applied for forward, semi-inverse, and full tomography problem. This is very interesting. The solution that we get is analytic and differentiable. We can add any regularization or prior that we would like, either differential operator, regularizer, or other, it doesn't matter. The algorithm is mesh-free and free-form domain, and we can extend that to a multi-dimensional and non-linear problem. Okay? And as I said, the sampling is an issue that should be further studied. And also error analysis is under current research. I mean, this is, I think, the most important thing. One should get a good error analysis for this method. Okay, thank you for your attention. And you can find both papers in the archive in the meantime. Should be published soon.
Thanks. Thanks a lot for a great talk. I'd like to remind the audience members, if anyone has a question, you can post them using the Q&A tool. And